am very excited here to present our OLMo project. So we have witnessed great progress in the past few years in large language models, where each model was building on top of findings of previous ones. But then most recently, research and development about language models have been closed off, okay? We all agree that we are here today, or our language models are here today because of open scientific research and because they were fully open at the beginning at least. But now what? Are we done with language modeling research? Of course not. There are so many problems that we need to address, and like we are seeing all this awesome work by all of you here at this conference. For example, we need to understand and study these language models scientifically, improve them, build their next generations, extend language models to other modalities, other domains like science, if you want a Nobel Prize, or health and other areas. Also, we want to use language models in real-world applications, build LM agents, solve fundamental problems in planning, reasoning, inference time inference. We want to mitigate their biases and risks, and importantly, work on efficiency issues. Okay, so to facilitate research about these language models and accelerate the science of them, we argue that we need language models that are truly open. We want every step of the process be transparent, fully reproducible, and accessible to a wider range of people and researchers. Or as one of partners puts it, AI Institute just working on language models, on proprietary language models, it's like astronomers researching about solar systems just by looking at their pictures with newspapers. Okay, but we have varying degrees of openness. So, of course, now we know all these models, we can download their weights, and then there are technical reports. We have worked with all these models, and we have learned a lot from these models. But we soon realized that is not enough for the purpose of truly understanding and scientifically analyzing what is going on in these models. Data is a very important piece. All details of the training recipe, and also checkpoints, like today someone was presenting how checkpoint progress works and how can we understand what effects are happening in model training. So with that, I would like to introduce our project OLMo, which is an open ecosystem that we try to understand and study and build language models at different stages. So OLMo is a piece of puzzle in the whole landscape of AI, where we have closed API models, or we have open weight models, infrastructures, GPUs, efficiency. Like, this is only one piece of puzzle. And through this project, we like to develop, study, and advance language models. We want to make sure that every step of the process is documented and fully reproducible, such that we can kind of target a wider audience of researchers. And hopefully through this, we can also improve AI public literacy. Okay, so I'm going to talk about 3 projects or 3 kind of threads of work that we've done in this setting, which is pre-training, building a multimodal open language model, and then post-training. So we have released these artifacts, OLMo, which is our language model, OLMOE, which is the mixture of expert version of OLMo, the training data set, and now our multimodal model, Molmo, and our post-training efforts under Tulu, which is like post-training llama-based model, and also building OLMo Instruct. And also all the toolkits and data and so on are also available through these artifacts. Okay. So through this project, we try to follow these 4 principles. We want it to be fully open. We want it to be scientific, meaning that we would thoroughly evaluate all our design choices and we would kind of release our findings. We also want to optimize quality versus cost. We want to get as high performance models as possible. And also, we want to be efficient in terms of data, in terms of training costs, and in terms of like the data structure or kind of model efficiency. Okay. First, let me give you a quick highlight of where we are. We are continually releasing OLMo models. When we started working on this project, starting it last year, Llama 2 was available, or like it came somewhere around the end of last year. And then we released our first model February this year, which was almost on par with Llama 2. We showed like this is a proof of concept. We can release data and it is working. Then in April, we released our next version, which we showed that with significant improvement over data and multi-stage training, we can outperform Llama 2, which was quite exciting. But immediately after, Llama 3 showed up. So now we have much more things to do. So in our current internal version, which we are hoping to release end of this month, across many benchmarks that we are evaluating, we are getting on par with Llama 3. Okay. So next is OLMOE, which is our first mixture of expert model, which we released last month. So first, again, I want to argue this is the most open MOE model you see on the diagram on the right, where everything like the model, all the checkpoints, data, and so on is fully available. And then MOE, why is it good? Because it is more efficient. So in this figure, I am plotting MMLU, which is like one of the most popular data sets to evaluating language models, versus the cost. And ideally, we want to be somewhere on the top left part of this image, right, on this graph. And we are very happy to see that OLMOE is getting there. OK, so now let's move on to more technical parts. And let's first start with pre-training. So many of you know that pre-training requires these three important things: data, what data to train the model on, which is the most secretive part of many of the even open weight models; training, take these data, produce those model weights, and then we want to do thorough evaluation across every step of the process. OK, so let's first talk about data, our pre-training corpus called dolma. So here is the list of data sets that are used to train some of the most kind of impactful language models to date. I don't want you to read all the details in this table. I just want to highlight that there are a lot of empty boxes because we have no idea what is there. There has been some previous work that focused on releasing pre-training corpora for training, but generally they are either at a smaller scale, like 1 trillion token max, or kind of less diverse domains. Until we introduced dolma last year, which is a corpus of mostly focused on English data, suitable for pre-training and consists of 3 trillion tokens. It covers diverse areas like web data, code, semantic scholar like scientific papers, books, and so on. We have all the details of how we processed and curated this data, and also the toolkit if you want to basically use that, generate or update some parts of the pre-training data for us. OK, so how does the data curation process work? I'm just going to give you a very brief overview. It usually consists of these three steps. We acquire data, like acquire web data, transform the data in a format that is suitable for pre-training, do a lot of experimentation, and then continue this for every source. So the interesting part is how to transform the data in a format that is suitable for pre-training. These are some efforts we've done, which we started with filtering for English, deduplicating by URL, applying a lot of quality classifiers and quality filters, followed by content filtering, which is removing toxic data or personal information, and then finally doing deduplications at multiple rounds. So I'm just like explaining it in a very hand-wavy way. Please look at the paper for details. And through this process, most of the data is kind of junk, not useful for pre-training. We go from 175 terabytes of common crawl to almost 3 terabytes or 3 trillion tokens of dolma. But one very important step during this process is thorough experimentation to understand if these filtering processes lead to good, high-quality data. So how do we do it? Again, remember, training these language models are expensive, so we want to train a smaller scale language model to see and expect and evaluate the impact of these data filtering processes. Okay? So we run a smaller scale models, we evaluate them in our Perplexity suite, and also in some selected benchmarks that we found useful to evaluate pre-trained model. We followed a lot of work from our friends and from Luther AI, CRFM, Databricks, and then created our own standard, OLMoE, which we are using to evaluate all our data filtering processes. And then we have also created this Molmo suite, which is a set of perplexity evaluations for a wide range of domains. And with that, we look at curves like this, like, okay, if this data change improves my model or not, and then we decide if we accept that change or not. So the data that we have curated up to this step is potentially high quality. We've done a lot of iterations, but still we are talking about 3 trillions of tokens. So it's really important to build tooling such that it enables us to dig deeper, understand what is exactly in the data. So Hannaneh, our amazing postdoc, led this project called What's in My Big Data, with the goal of providing these functionalities of counting and search of big corpora, not just dolma, but other available open data sets. And then we can use that to do lots of analysis, like decontamination, which is a very important thing. Like we want to make sure test sets are not contaminated in training data. Also, what are the domain distributions? What are the common n-grams, and so on? So for example, through that, we realized some of the most common n-grams in the C4 dataset are a sequence of question marks, or chess website is one of the most common websites that you can find in all these pre-training corpora. So like this might hint at the chess capabilities of some of these models. But we are talking about trillions of tokens, right? So we need to have much more efficient search algorithms, right? So previously we used Elasticsearch. Today you heard from my amazing student, Jia Chen, who developed Infinigram, where it helps to more efficiently search and count tokens in these gigantic corpora. For example, we are able to reliably count the number of these phrases, what is the next token that is coming after university, and also search phrases like university of. So you can play with the demo, you can search your own corpora as well. But this is very helpful for us because now we have built OLMo Playground, which we are about to release soon, that for a given question, like write a short bio of Barack Obama, we'd be able to kind of link longest sequence of text or n-grams to the documents that the model actually copied from, right? So we find some phrases and then find corresponding documents. So it kind of, we don't call it attribution, we call it corpus link, because now we are able to connect these pieces to the actual, kind of to where they are copied from. Okay, so since our release of dolma, we have seen a lot of efforts from the community working on building and improving pre-training corpora. So we have Findware from Hugging Face, DataCompLM from our friends at University of Washington, and TXT360 from the LLM 360 team. So we are seeing all these amazing efforts, and we are basically building on these new iterations of pre-training data. So now let's move on to the second stage. When the pre-training corpus is ready, we want to build a model. Again, to highlight, we are obviously using a decoder-only transformer architecture. We have OLMo at 1 billion and 7 billion parameter trains for 2 to 4 trillion tokens. We also have our OLMOE mixture of expert model, and our design principle, we want to optimize quality versus compute. Okay, so when you want to build or train these language models, there are many configurations that you need to tune in order to have a really good model. So I don't want you to read all these details, but there are these many parameters you need to tune. And we are looking at other open weight models, and everybody has made different design choices. Okay, so there are too many things to try. We know training these models is quite expensive, or it's very expensive. For example, if you want to train a 7B model up to 5 trillion token, it costs more than $300,000. So it's very important to be accurate, not make a lot of mistakes. So our principle, we want to optimize quality versus cost. And we are taking 3 approaches. One, we have developed the scaling laws to predict task accuracies from smaller trained models. we have improved our training pipelines a lot, and we are making more and more stable training. And then we are focusing on efficient architectures. Okay, so a scaling law goal, we want to predict task accuracy of a large model given smaller trained models. Okay, so what does that mean? For a given n, which is a model size, and d, which is training tokens, we want to map this n and d to a task accuracy. How do we do it? We take this two-step approach. First, we want to predict the task-specific loss, like the loss that is really particular to that task, for a given number of tokens, and then predict the task performance given the task loss. So Llama 3 also has done that following their technical report. In order to predict the task loss, we are using chinchilla equation, which is kind of we are predicting loss with respect to n and d, which is the number of tokens and the size of the model. And then how do we transform a task, like for example, a multiple choice task, into a task loss? It is on how we can predict that ground truth, right? So it's kind of like a very nice perplexity evaluation. And then the goal is to fit all these parameters. So we've done that. For example, you are seeing this curve for MMLU. We train models for up to 1 billion model with different number of tokens, and then we predict the accuracy, or sorry, the task loss for a model that is trained up to 3 billion tokens, 3 billion model parameter, or 7 billion model parameter. Then in the next step, we predict task performance. How do we do that? We fit a sigmoid function. So in this, I'm showing you Hella's swag, a 5-shot curve, where we are plotting task score, which is like the actual task accuracy, versus task loss. The intuition behind the sigmoid function is when we are somewhere over there on the left part, the task loss is high, meaning that the task accuracy is very low. And then when the task loss gets better and better, closer to 0, we're going to say, OK, we have solved the task. Again, we train models up to 1 billion parameter, and then predict for larger models. We chain these two steps together, and then finally have a curve of task score versus the number of tokens. Results are really good. On average, we are about 97% accurate in predicting task accuracy. And for some tasks like MMLU, we are like 99% accurate. So it's like less than 1% error on predicting task accuracy, which is actually a really good signal on deciding when is a good time to stop curating the data, let's train a bigger model. OK, so next thing, we should and we are improving our training pipelines. Why? A mistake in pre-training or like bad selection of the data is costly. It can cost millions of dollars if you train bigger and bigger models. Let's look at this curve, for example. This is not such a nice loss function, right? At the end, we are seeing some sort of loss divergence, and the things that we did to save the model didn't work. And then after that, we are not seeing any task improvement, right? Any task accuracy improvement. So let's hear some stories, some mistakes that we did throughout. So let's look at this loss curve. It doesn't look nice, right? You expect a loss curve to be very nice and smooth, but like we have this wavy loss. Okay, so we dug deeper to understand what is the source of this. And we realized it actually goes back to this subroutine where we shuffle the data, we make kind of data batches, we pass it to training step. And then digging deeper, we realize actually the source is that line of code, which we are calling the random permutation from PyTorch. So I'm simplifying the problem, but basically at the end, what we observed was it was actually generating this kind of wavy curve. It was pseudo-random. It wasn't actually generating a really list of random sequences. Okay, so we solved our problem by calling random function from NumPy, but that was a bug. We reported PyTorch has fixed it, but this is kind of these type of issues also exist in training, and it's very hard to debug them. Our next issue, fast spikes. So what does it have to do with a microwave? During some round of trainings, we were seeing this loss function. okay? So lots of spikes, doesn't look good. We call them fast spikes because like when we are training, you see these spikes, but then the model recovers, continue where it was, okay? So we thought it's most likely related to that batch of training data, okay? Something is going on in that batch. After digging deeper, we realized it's basically coming from this subreddit, which is called microwave gangs, where people actually were typing AMS followed by a beep. And suddenly it kind of skipped our training cleaning, so yeah. Okay. So I keep saying we need to improve our training infrastructure because you want to train these models faster and faster, right? So our original OLMo was trained on LUMI infrastructure, and it was quite slow, like 750 tokens per second. We made lots of improvement, like better data parallelism, pipeline parallelism, and so on. And most recently, we can train about 13,000 tokens per second, which has quite improved our speed of training a 7B model, for example. That, like with this kind of improved training pipelines, together with a lot of efforts that we had done in improving our training stabilities, removing spikes, cleaning our data better, and so on, our latest version of OLMo, which you see this pink line, we could increase the context lengths, and we could increase the number of tokens from like reliably training from 2T to 4T. We could have continued, we just ran out of compute budget. But yeah, and as you can see, also we are seeing much improvements in like MMLU scores and so on. Okay, good. So now, let's move on to our next efforts on building more efficient architectures. In particular, we released OLMOE, which is a mixture of expert model, fully open. And again, I mentioned it, we want to be on top left corner of this figure. And fortunately, we are getting there. Here, I'm showing the kind of larger scope evaluations in 3 buckets. First bucket, I'm showing models at like 7 to 10 billion or to 9 billion parameter. In the second bucket, we are looking at numbers when there are 2 to 3 active parameters, 3 billion active parameters. And the last bucket, we are seeing models with 1 billion or so active parameters. And as you can see, OLMOE is like significantly higher than all other 1 billion active parameters, and also really rivaling the models with bigger kind of number of active parameters. So, but first, let me justify why we need mixture of experts. These curves show training loss, validation loss, and HellaSwag accuracy for 2 models, a dense model and an MOE model. MOE is like the pink one, okay? And as you see here, we would achieve same accuracy or same loss with less number of tokens or less number of training flops. So it is good, right? So more efficiently, you can get to the same accuracy. But what does it mean? Like, what does it mean to be a mixture of expert? It means that we look at the feed-forward network in the transformer architecture, replace it with an MOE module. How does it work? It has a router function which tries to pass tokens to individual experts. Like, each expert would be responsible for one of these tokens. Okay, so this doesn't seem complicated. So we implemented this. And we were expecting to get really good results. But this is the outcome. A super ugly loss curve, super spiky. Even though the model was quite stable at 7B dense style, when we moved to MOE, this was the result. So this was the training loss. This was the validation loss, the HellaSwag, MMLU. Everything was bad, like so disappointing. So how did we fix it? Lots and lots of ablations, analysis, and kind of I'm showing the summary. Please check out the paper for details. We improved initialization. We replaced our layer normalization from non-parametric to RMS norm. So you are seeing that on this part, which shows the kind of how we have removed the spikes in the pink curve and this figure actually shows the gradients and how they are not spiky anymore. We've also added a query key normalization. Again, over there, you are seeing hello swag performance of having QK norm in the pink part, and then the blue part, which was a spiky. So I'm removing a lot of other details here. So we also did some MOE-specific analysis. We realized when we add load balancing regularization, it actually helps a lot in improving the performance. So on the left, you see the model in a sense that the percentage of tokens that are being routed to specific experts when we do not use load balancing. And as you see, almost 2 experts are getting all the tokens. And in the other part, you see when load balancing is involved. And now you see a really nice kind of mix of tokens being routed to a lot of these different experts. So load balancing is good. Another interesting observation we had was it is much better to use fine-grained expert rather than just kind of a smaller number of experts. So these figures show MMLU and hello swag accuracies on cases where we use 8 dark blue, 32 light blue, and 64 experts, the pink one. And in all cases, we noticed that when we use more fine-grained experts, the numbers and the performances are higher. So putting all these together, now we have these nice curves, which I'm showing the training loss, super stable, the validation loss on our perplexity suite. And as you see, all of them seem very stable. Another nice thing about our fully open MOE model is that now we are able to provide analysis because we have access to the data, right? So the data is available. Now we can provide a lot of analysis of why it is working, how it is working, and so on. So this is, for example, one of our interesting analyses that we've done is we are looking at different domains like GitHub, Archive, Wikipedia, books, C4, and so on. And then we want to see how tokens in these domains are being routed to different experts. Okay, so x-axis shows the indices of our experts. Y-axis is the percentage of tokens that are routed to those tokens. So for example, when we see higher numbers like these spikes, it means a big batch of tokens from that domain are passed to that part, are routed to that particular expert. We started investigating some of these kind of spikes, and like these are some of the tokens that are passed to, for example, expert number 8, which are things like grandmother, brother, daughter, mom, father, wife, husband. So it's kind of a family expert. Or this one, which is things like square, gigahertz, pixels, centimeter, and so on, which we thought these are probably metric or unit type expert. So this is quite interesting. We've done a lot of analysis in the paper. Please feel free to look at them or even add more analysis. So another nice thing that we are quite enjoying it with our OLMoE architecture is that now we can run it on device, okay? Because it has only 1 billion active parameters, and therefore we build the app by connecting it to Llama CPP. And now we can like query it on our cell phone and then get responses. And the speed is not bad. It is generating 110 tokens per second. Obviously, we can improve it. So we are quite excited to see that people in the community are using OLMo in kind of studying language models scientifically or even improving it. So for example, we've seen papers that try to attribute model behaviors to pre-training data. People are using OLMo as kind of to design policies regarding language modeling development, or trying to understand what are the effects of fine-tuning and the base model, like on top of base model, what things are changed, what forgetting happens. Developing new architectures like Zamba, SOAP, and so on, that they are all building on the OLMo code base. And also, interestingly, people are using our checkpoints on how models acquiring knowledge during training or evaluating different checkpoints or kind of developing scaling laws using all these checkpoints. So we are very excited to see that community is using these models. Okay, so I want to move on to the next section, which is multimodal language model. This is our most recent release. We have recently released Molmo, which is multimodal open language model. So this is mostly an NLP crowd, so let me give a very quick overview how we build this model. It is a late fusion multimodal model, okay? We start with an off-the-shelf vision encoder, okay, like CLIP, and off-the-shelf language model, and then for a given image, and like it can also have text, like point to Mount Rainier here, we generate the kind of the completion, where what we generate here is the XY coordinate of the pointing of that place that we need to point, okay? So we obtain tokens, or like we obtain different patches from the image, okay? Pass them through our vision encoder, obtain image tokens. If we have text, we also tokenize it, and then we pass all these to a large language model, and then we generate the output, the completion. Okay, again, here, this is XY coordinates. So through this, we released a family of models at different sizes, from 1 billion MOE to 72 billion. So our vision backbone, CLIP, is CLIP. Like, it is not open, like we admit that. And we have used different language models. For 1B and 7B, we build on our OLMo stack, and for 72B, we are using QN72. We are evaluating these models on 11 academic benchmarks, and also we have done very extensive human preference evaluations. In a sense, we have worked with about 900 users, and we collected more than 300K pairs of comparisons between all these different vision language models that exist, or at least we could find. How do we compare with other models? So when we compare our models on these academic benchmarks and ELO rating with the closed API models, we are very excited to see that we are very much on par. Even the MolMoE, which is the kind of OLMoE backbone of the multimodal model, performing and outperforming Cloud Opus and Haiku. This is actually very exciting to see. Comparing with other open weight models, we are significantly better, especially in the ELO rating and human evaluations. Like, for example, comparing with QuenVL that just recently released, we are, like you can see it on top, we are significantly better. So I'm mixing up model sizes a little bit here. So of course, 72B models are better, but like we are outperforming a lot of these open weight models. When we released this, it was like on the exact same date that Llama 3.2 came, like a few hours after us, and we even hadn't started comparing OLMo with Llama 3.2, but we were very excited that people in the community started comparing Llama 3.2 with our models on all these academic benchmarks, showing Molmo outperforming in a lot of these benchmarks already. We have also done human preference analysis. And again, we are very excited to see Molmo is kind of outperforming Llama 3.2. Even we have 72 billion, Llama 3.2 is 90 billion parameter. So what is the secret sauce? I'm just saying it's really good. So you need to have high quality image text pair data to train this model, okay? So in Llama 3.1 paper, they are saying that they have trained on 6 billion image text pairs of data, okay? In comparison, like this is that data, and in comparison, that is our Pixmo data. I'm pretty sure people who are sitting on the back don't see it. But let's zoom in. Like we are just using 700K really high quality image text pairs. So again, chiming in our quality versus cost optimization. But let me say, what do I mean by high quality? When you look at images on the web, for an image like this, the description is something like this: pink, Japan, image, or something, right? Or in the bottom one, we say, love this winter picture. However, the data that we've collected is something like this. For a kind of neutral image like this, we have very detailed annotations of what is going on in this image. So our annotators mention this photograph captures a well-organized work desk, then continues, say, to the right of the monitors, a black mouse rests, and then talking about the background in the next paragraph and so on. So there's so much text going on about describing all details in this image. Now, for an image like this, you would imagine there are not much to say, but this is our annotation. Like, there are so much details about these are the icons. We think these icons are this and that and so on. So there are a lot of this. But how did we collect this data? We realized that humans don't like to type as much as they are okay to speak. So we gave them instructions, and we told them you should talk 60 to 90 seconds per image. And then we use language, like they talked, and like we were looking at these outcomes and the story. They talk a lot about even a very kind of deserted image. And then we use language models to kind of change the format a little bit, annotate, and then kind of combine and clean up the text. So we combined this Pixmo data with a lot of data on pointing, and then combined with some instruction relevant data, which are like question answering and so on, and then finally trained our model. One new feature that we've added to Molmo compared to other language vision models is the pointing ability. So Molmo can answer, or like basically we've collected data, and now it can do things like point to the menu, or it can like take actions because now it can interact with these web environments. Point to where I can see these search options, or point to where I can mid-size data set, which is quite interesting to kind of point in the middle of that line. We are using pointing because it has this pointing capability. It's much more accurate in grounding to images, like counting. For example, count the number of votes that are here, or count to the kind of path of this bus. And that was quite interesting for the people and for other people, and they've looked at many different kind of applications and images shared with Molmo on what other type of counting questions. Okay, so with that, I would like to show you this video. One more nice thing about working on vision language domain is you can have a video kind of show the capability. So now let me show you this video kind of pointing to Molmo capabilities. I tried, it worked earlier. Of course it won't work now. Okay. That's fine. Okay. That's okay. So you can go to this link. You can go to this link and play with the demo and also see the video online. So going back to our promise that we want to be fully open, we are comparing all our Molmo components with closed API models. So everything except the kind of vision backbone is open, and also the 72B model. Also, compared to open weight models, we are releasing all our vision language data as well, which is also very exciting. And yeah, so we love to continue making more and more of these high quality data and releasing it, explaining it why these multimodal models work well. Okay, so moving on to my next topic, which is how to post-train these language models. So when the language models are ready, or they are coming out of the pre-training phase, they are not ready to be used for end applications. They are not safe, or like less safe, and they are probably not that good in following human instructions, especially at a smaller scale. So we need for them to go through some post-training stages. After that, we teach them how to follow natural language instructions, be aware of harmful behavior, respond to human queries, and so on. So our team has been active in this domain since 2020, 2021. So our first project called Natural Instruction and Supernatural Instruction, led by Daniel, Ijong, and Swarup, we tried to unify a lot of NLP tasks such that for a given instruction and an input, we want to generate an output, right? So we had this kind of, now it's very obvious, but we had kind of this intuition that when a lot of these NLP tasks are pretty much doing the same thing, let's unify them. And then we go through this so-called instruction tuning stage. And there were a few concurrent work back then, like T0 from Hugging Face, that they were all like very related, very amazing work. So we made a demo back then and realized it is working really well on this type of question answering, like short type text generation. However, it is not doing this kind of real open-ended tasks. And it is very hard to collect training data that way. Then Ijong came up with this very cool idea of why I don't generate synthetic data using a language model to generate synthetic data. And he proposed the self-instruct framework, where we synthetically generate lots of prompts, input and output, right? And we were using, I think, GPT-3 back then. Of course, the data quality was not that great. So this methodology basically received really well with the community. And then soon in like 2023, we saw lots and lots of synthetically generated data set, and other groups started generating human annotated. And again, open source, again, collaborated a lot to put lots and lots of all these instruction type data. So we thought, okay, now we have too many data. Which of these data points are high quality? Which ones are helpful? Should we mix all of them? So we introduced the Tulu project, which back then we trained on, I don't remember, was it Llama or Llama 2, on how to look at all these instruction available data, put them together, and then build the best model possible. So we soon realized that the quality of those data matters. When you look, like the type of data that are being added matters. So the things that are like very obvious now. Then in our next version, we incorporated a preference tuning, in particular DPO. And we brought that into the post-training stage, which we showed now we can scale up a 70B model, instruction tune, and also do preference tuning at 70 billion parameter. The model performed really well in 2023, and on Alpaca eval, and also in like a chatbot arena, it performed really well behind GPT-4, but better than ChatGPT, which was very exciting to us. Then we said, okay, everybody is using PPO, so let's bring in PPO instead of DPO. And of course, this is like online, and it's much harder to implement and so on. So we built a pipeline with amazing people here, or some of them on the audience, and we started comparing all different preference tuning algorithms, like DPO and PPO. So a lot of you agree that PPO performs much better compared to DPO, but it's much harder to scale up, right? So like throughput is less, it has more memory usage and so on. So it's a trade-off. So what we've learned so far is now we do a lot of investigations under DPO setting or rejection sampling, and then probably once we want to build a final model, we incorporate PPO during training. So now we are working on Tulu 3, on releasing Tulu 3, hopefully in a month or so. And now we have reflected back on what is going on, what things worked, what things didn't work. And we are looking at identifying core skills that we want to improve, for example, coding, reasoning, math, instruction following. We look at many different ways that you can have data: human annotation, expert annotation, synthetically generated, what type of preference data do we need, and how do we mix it? So like this mixing strategy is very important, because once you improve on some core skill, like right now we have amazing math model, but do they perform well on, for example, instruction following? Probably not, right? So how do we mix all these such that the models perform well? And then we also look at many different methods on how do we do better multitask training, rejection sampling, all these preference tuning methods. So stay tuned. Hopefully we'll release the model soon. The results are very promising so far. Okay, and all this while we are maintaining openness. In some external study, some group actually ranked OLMo 7B in Struck as the most fully open model out there. So we are very excited. So to summarize, I talked about our efforts in pre-training, multimodal, and post-training. And these are some of the artifacts. Please check our website if you are interested in using them. Again, we are excited that you are using it at the time of the release. Both OLMo and dolma were the most popular data sets and model in the Hugging phase. And also in the past 6 months, we have had more than 2 million downloads. I want to again remind everyone that OLMo is just one piece of puzzle in the whole landscape of AI, and there are many more to have really good, better frontier models. So to remind you about all these problems that the community can work on, and I just want to highlight some of the interesting directions that my group is excited. We love to extend language models beyond text. We started with multimodal. In particular, we are very much excited about language models for science, both at inference stage, like this project that Akari is leading, on building multi-paper question answering system, on doing a much better literature survey and providing insightful comments. And also we are excited to see Cosmic AI has been developed by University of Texas researcher building on OLMo, like building AI for astronomy data. It is very important to work on mitigating risks and biases and work on safety of these language models. These are some work led by amazing people at UW and AI2, like Nuha and Pfizer leading some of these efforts. And then we are very excited on not just relying on transformer architectures or even just like this kind of pipeline of data pre-training evaluation. We need to think on building next generation of language model. So one particular direction that we are considering is this. So today's language models, when you have a query at inference time, you expect this model to memorize everything and respond queries to you, okay? This should be perfect. It should know everything. This is very expensive. It is very hard to remember all these details, and it is not flexible, right? We keep updating our data, and it is very hard to retrain everything from scratch. So we are saying that instead of discarding data during training, we like to keep data at inference. And now we can augment it with retrieval. Then we would be able to locate the data and then reason about it, use these parameters of the model to reason about it. So then we don't need to remember all the details, and then we can kind of grow seamlessly. So retrieval-based LMs could be a solution. So Seiwan and Akari are kind of leaders in this effort. The idea is for a given query, we would like to retrieve a few documents that are related, and then use language models to kind of generate tokens based on retrieved documents. And there are many things that need to be resolved here: improving retrieval, improving language models, making sure hallucinations doesn't happen, and so on and so forth. There has also been a lot of work in the community, for example, by Danchi's group here, and many more. So given these new functionalities that these retrieval-based language models provide for us, we would be able to do better data attribution. So we can potentially explore ideas on how to build models that are better in in using data much more cleverly, and also be much more responsible on using this data. Because now we can have better data attribution and can have opt-out. And then finally, we are very excited in the direction of using language models in real world. So of course, we are doing a lot of research in language models, but they are kind of meaningless in isolation. They would work with a really large collection of other tools, other models, and so on. So we love to work toward learnable AI systems, where we like to have some sort of composite AI planner that decides when to rely on tools, when to rely on specialized learned models, or like maybe general purpose model, when to bring in human experts, and how to interact with environments. Or in particular, we need to have a lot better orchestration between language model, different types of language model. We need to build better agents. This would enable us have better real-world impact. But one thing that we need to do is move from very static kind of agentic environment that we currently have to more general purpose AI agents. But for that, because we are talking about a lot of systems to be integrated together, we really need to work on more efficient model. So with that, I really love to thank my team at UW and AI2 and many more collaborators who were all helping in this project. Thank you.